Hello again, I'm David, and I'll be talking about related rates. The related rates bit of the course, when I looked at your lecture notes, was very short. And anytime there's something that's very short in your lecture notes, a useful question to ask yourself is, why is this here? You would like to ask yourself that for many things, why am I here? But why is this here in the course? And what you want to do, well, you don't know why it's here yet, but I'm going to tell you a few useful things. If you are doing, say, mechanical engineering or physics, one of the reasons related rates is here is because that's like the bread and butter for dynamics. So if you are ever going to do the course dynamics, related rates is what that is all about. And that's why one of the reasons it's here in the course. The other reason is, of course, that they wanted to put something in so that they could justify the formula for the slope of the tangent to a curve, because they use related rates to justify that formula. So mathematicians have this need to justify things, to say, yes, there's a good reason we're doing it this way, and they feel the need to put in a little topic on related rates because that's their justification of it. Okay, so that's the reason it's there. It's there to justify that. But the other reason it's there is that if you're doing any kind of physics that is investigating the motion of things, so dynamics, as opposed to investigating the stillness of things, which is called statics, if you're doing anything about that, and in fact a course would say dynamics in the title, you'll be using these concepts of related rates from the get-go. So they put it in Maths 1M so that those people who are doing dynamics without having done Maths 1A will be better off. That's why it's there. Okay, but otherwise it's one of those things. So the big idea of related rates is that in lots of situations everything is changing, and all of those rates of change are related to each other. Everything is changing, and all those changes are related. And this everything is changing is important. And it's easier to talk about with an example. When I did related rates at school, I remember very clearly this example of a balloon that is blowing up, and it's a sphere, and we were supposed to be interested in the rate of change of the volume compared to the rate of change of the surface area. And you had an example like that in your lecture notes, but it was a cube. Okay. So in most situations, everything is changing and all those changes are related to each other. And if I say I would like to know what the rate of change of something is when time is 2 seconds, or when the radius is 5 centimeters, it's important to remember that that is just one option for the possible times or radiuses that could have been, and I'm focusing on a specific one at the moment. So in all of these related rates problems, everything has to be regarded as being changing all the time, and only at the last second do you put in any specific numbers. That's my advice for these things. So, a sphere. Our sphere is growing. Cool. And I would like to know, our sphere is growing. Good-o. So what is the rate of change of the volume when the radius is 2 centimeters? Okay, just a second. What is the rate of change of the volume when the radius is 2 centimetres? If the radius is changing at 0.3 centimetres per second at that moment. Okay, so let's read that again. I've got a sphere that it's growing. What's the rate of change of the volume when the radius is 2 centimetres if the radius is changing at 0.3 centimetres per second at that moment? So let's think about what's changing here. The radius of the sphere is changing, the surface area of the sphere is changing, the volume of the sphere is changing, you know, the circumference of the sphere is changing. Everything is changing continuously. Time is changing. Time is moving along. Everything is changing. But I can figure out how those changes are related to each other by using what the chain rule. I'm just doing an example of this. You need to know how those numbers are related to each other first. That is the volume of a sphere. And the r is the radius. That's the formula for the volume of a sphere. And that at least relates those numbers. At any given moment, if I knew what the radius was, I could figure out the volume. At any given moment, if I knew what the volume was, I could figure out the radius. But the problem is that the r is constantly changing, and so is the v. That's my problem. And I want to figure out the speed at which the v is changing, rate at which the v is changing, at a specific moment. Now, I haven't been told what time that is. I haven't been told the time that that happens. All I have been told is the radius at which it happens. So it must be possible to figure this out without knowing what the time is. That's one of the key things. So, okay. Well, I'm going to do this thing where I know that everything's a function of time. R is changing when time changes. V is changing when time changes, but only really because R is changing first. So I can imagine using the chain rule for this. That's how quickly V changes when time changes. And then let's work our way through this. 4/3 and pi are constants. And constants that are multiplied on are still there after I do a derivative. So they'll still be there. That's a times sign. Now, I don't really know the formula for r in terms of t. I do know that when t changes, r is changing. So presumably there's some sort of formula that will tell me, given a specific time, what the r is. But I don't know what that is. But that's okay, because I can use the same ideas of the chain rule. I know that if this was a t, the derivative would be 3t squared. But it's not a t, which means I have to use the chain rule. This thing here is a function of t. So, since it's not a t, but it's actually an r, the chain rule tells me I'm going to have to times by the derivative of what's there. And I do that all the time when I do derivatives. If I did like cos of like something, right, I'd do minus sine, and then the thing would be there, and then I'd times by the derivative of the inside. It's the same idea. It's just that the r looks like a letter at the moment, but it's actually hidden a function of t. There's some formula there that I don't know that I'm going to have to figure out later. So this is where I am at the moment. I have that dv on dt is 4/3 of pi times 3 times r squared times dr on dt. Now here's the thing. I will see what I can do. They've told me that at this exact, so this is changing. So as the radius changes, the rate of change of t will change. The bigger r is, the faster the volume is changing, because this gets bigger. But it depends on how quickly the radius is changing at this moment as well. So let's see, at this moment the radius is 2 centimetres at this exact moment. And at this moment, the radius is changing at 0.3 centimetres per second. So I can write that information down. At this moment, the radius is 2, and the rate of change of the radius is 0.3. Now, if I was doing this in science, I would, and it even counts in maths, I would make sure that those were in the same units before I moved on. If one was in metres and the other one was in centimetres, I need to convert them. Now, your maths lecturers are unlikely to make you to do that trick to you, but your science and physics, physics and engineering lecturers, yes, they will do that trick to you. So keep an eye out for it. Because mathematicians, while units are important to them, it's the derivatives that are more important today. So, yes. So, at this moment, so not to say that dv on dt is always this answer I'm going to get, it's just that at this exact moment, this is going to be the dv on dt. So it's going to be 4/3 times pi times 3 times 0.3 squared times, no, wrong one, times 2 squared times 0.3, because the r is 2 and the other one is 0.3. And so at this time, I would just calculate that in my calculator. I suppose I could do as much as I could. This 3 will cancel with that 3. I could have cancelled that way earlier. I'm sorry about that. This 4 times 4 would be 16. 16 times 0.3 would be 4.8. Yes. I think. Let's check that. Yes, okay. 4.8 times pi. Which is approximately 15.08 centimetres cubed per second. Units are important, so I would put the centimetres cubed and the seconds in there. Okay. The only reason I know that 16 times 3 is 48 is because that's how many cards I can fit on a strip of cardboard when I print my own games. So I can fit 16 on a strip, and a big piece of cardboard fits 3 A4 strips wide strips into it. So I can fit 48 cards on a single piece of cardboard. That's why I know, by the way. Similar to how I know that 3 times 17 is 51, because that's how many blocks there are in a Jenga set. Yes. And that's, I don't know, that's pretty much all there is to related rates, except that there's a couple of moments where they've used a bit of weird terminology, and it's always worth just pulling apart what that means. I may do another example as well. This example here I found rather interesting. It's similar to mine, only it's about a cube, and it said the length of each side of a cube is increased at a constant rate. Which is greater, the relative rate of change of the volume of the cube or the relative change of the surface area of the cube? And that's a weird old terminology that hasn't really been defined in your notes. And so I just thought that any time a terminology comes up when you read your notes, you should have a handle on what it means. What is relative change? Like relative rate of change? It just would be worth knowing the meaning of that. So they're saying the relative rate of change of volume is 1 over v times dv on dt, and the relative rate of change of surface area would be 1 over a times dA on dt. That's a bit puzzling to me, but I did figure it out. Relative rate of change of some anything is the change divided by the quantity itself, basically. So that's why the 1 over v and the 1 over a. So it's a little bit like relative errors over in science. It's the change divided by the original. Just in case it ever comes up. Now, my purpose there was not to tell you what that means, but to say that you can usually, from context, figure out what something is, and it's useful for any terminology that comes up for you to know what it means. Oh wow, that's an interesting one, isn't it? Does anyone have any specific problems that they have seen of this type that they would like me to go through? Because otherwise I'll just do one more before I sign off for lunch. Most people at this stage in other courses would pull out a past exam, but you don't have very many to refer to in Maths 1M, unfortunately. Well, at least not for this. This is new. Like complex numbers has been in Maths 1M for 40 years, but relative rates of change is new. Okay, so technically with any of these things you can do anything. Anything that you can do with ordinary derivatives you can do with any of these things. So just as another example, the volume of like a cone is pi r squared h, radius r, height h. It is possible to change two things simultaneously. You're just going to use all the same sort of reasoning. So we could say, at a rate of 2 meters per second, and the height is changing at a rate of like -1 meter per second. So radius is increasing and height is decreasing. At the moment, grammatically that is bad, I'm sorry. At the moment when radius is 6 meters and height is 3 meters, how fast is volume changing? So you could do that. Radius is changing at the 2 meters per second, height is changing at -1 meters per second, the radius is currently 6 and the height is currently 3. How fast is the volume changing? I can figure that out, even though there's a whole lot of things going on there. The same thing is going on in the other ones. My goal is to figure out how fast the volume is changing. When you're faced with any problem, one of the first things you should do is figure out what the goal is. How fast is volume changing? Cool, that's dV on dt. That's what I want. That's what I want at this moment, dV on dt. Okay, so my original formula is pi r squared h, and I want dV on dt. All right. But look, everything is changing. The radius is changing. The height is changing. They're both changing. So really, they're both changing with time. So they both count as functions. Now, I would like there to be formulas for how h is changing with t, but I don't have them. So all I can do is know that they are functions of t and know that they're multiplied together. So if I was doing this when there were brackets with t's in them, I would use the product rule. That's what I would use, because they're both times together. And I would even use the chain rule too. But I'm going to imagine this as these two things. The product rule says that I'll keep this one and differentiate this one. And then I'll differentiate this one and keep this one. That's the product rule. I'm imagining that the r squared, the pi r squared, and the h are both functions of time, and so I have to use the product rule to do it. Now here, this derivative, the pi is a constant, so it will still be there afterwards. The derivative of r squared would be 2r if r was the function I was interested in, but because it's actually t I'm interested in, I also have to times by the derivative of r. This is the sort of thing that goes on in science, because we never actually have a formula for how these things are related to each other in science. They're just all changing simultaneously, so we're just going to have to run with this. And now I have everything I need to calculate the thing I was asked to calculate. Two pi r h. Yep. So at this moment, r is 6, h is 3, dr on dt is 2, and dh on dt is -1. So dv, dv on dt, can I see both of those lines at once? I can. Will be pi times 6 squared times -1 plus 2 times 2 pi times 6 times 3 times 2. Just putting everything in from what I've done there. That's 6, that's -1, that's 6, that's 3, and that's 2. And that'll be whatever it is. I think. So you've got -36 here, 3 times 2 is 6, so that's 6 squared again. So you've got -6 squared plus 2 lots of 6 squared, so that would be 1 lot of 6 squared, which is whatever it is. Everything was in meters. Yeah. In physics, they do some other very sweet little tricks when they do this, and they will come up quite early in the piece if you do dynamics. Feel free to have a chat to us at the Maths Learning Centre about them. Don't forget the Maths Learning Centre is open from 10 a.m. until 4 p.m. all the way to the end of the exam period, except on public holidays and weekends, but it's not open next Monday, but it will be open all the rest of the time. I have another seminar next week for you, and I will do whatever you want. Even if it's just turning up and taking requests of questions to do, I will do them. Thank you very much, and good luck. I will see you around.